So today we are going to speak about blockchain mining algorithms. We are going to take the Bitcoin blockchain as an example throughout the session. So most of the examples are going to be related to the blockchain of Bitcoin. First of all, I would like to thank SoftUni to giving me the opportunity to be here. Who am I? My name is ORLIN. I'm a front-end developer. I work for Tradelogic. It's another fintech provider. We have another project there which is blockchain related. It's called CrowdWiz, where I'm the main Solidity developer actually. I used to be a trainer a couple of years ago, and this is actually my first training session since 2012 or 13, something like this. At this time I was traveling around the world working for Ipsos. It's a market research company. Pretty much that's it. I'm a blockchain enthusiast. I'm a miner myself. So it's pretty interesting to me to get deep into the blockchain and mining as a topic. Okay, so today we're going to stop on the following topics. We're going to see what is actually mining under the hood of the Bitcoin blockchain. We are going to compare some proof algorithms. There are consensus algorithms, proof of work, proof of stake. We are going to see each one of them. Proof of work is actually the one that we are going to see, and it's implemented in the Bitcoin protocol as algorithm. We're going to see what is actually mining Bitcoin. We're going to stop and see the rewards that these miners actually get. We're going to do some math by calculating the maximum amount of Bitcoins that are going to be available in, let's say, 20 years, something like this. We're going to see what is solo versus pool mining. Do we have a chance to mine solo, or we have to take the pool mining as an option? In the end, we're going to see how the cryptographic algorithm works under the Bitcoin blockchain. We are going to do it with paper and pencil. We are going to have the inputs. We are going to apply SHA-256 on them. We are going to see what is the mechanism while we have an input and how we get the final output, which is with a fixed length. Maybe with all the craze lately about the Bitcoin, Ethereum, it's easy to wonder what is this fuss all about. So today we are going to understand what's actually mining and the technique behind it. What is cryptocurrency mining actually? First of all, it might be a little confusing at first, but mining, when it comes to Bitcoin blockchain, Ethereum blockchain, it's about securing the blockchain. I mean that we know that we should get a consensus about who could create a block, who could add block to the blockchain. So we have to make sure that we have a consensus and the blocks that are added to the chain are really valid and the information there is real. First of all, miners take care about the so-called double spending. In the real world, if you pay for something, if you send money, there's a third-party organizations that take care of this not to happen. They take your money, they save them, they send the money back with some fee. So here, this is solved by the miners. They validate all the transactions. They make bunch of transactions into a block and they validate it. We're going to see later what it's actually to validate a transaction and validate a block itself, where we have a bunch of transactions actually. Mining is not about creating coins only, as most of the guys are thinking. As it is said, it's the mechanism that allows the blockchain to be really decentralized security. I mean that we have no authority that stands behind it. Every miner or computing hardware computer is a miner actually, and validates all the transactions and keeps the blockchain up to date. It keeps it secure. In this matter, it's just a system without a central authority, as I said. Okay, mining serves as two purposes. First of it is to verify the transactions and avoid the so-called double spending. The second is creating new digital currency. Bitcoin, in the very beginning, for every block that is mined, there's a reward for the miner. In the very beginning, it was like 50 Bitcoins. Currently, the award is 12.5 Bitcoins. And the amount, the reward for validating a block is going to decrease until it gets zero. Around 2040, we are not going to have new Bitcoins. So we are going to hit the cap. We are going to have around 21 million Bitcoins. And this is pretty much it. At that point, all the miners inside the network are not going to get a reward for mining. Everything they are going to receive is going to be some transaction fees. That's all. That's the second thing. First of all, we need to understand a bit of cryptography and hashing in order to learn how mining works actually. We are going to see some examples later about them. And as I said, in the end, we are going to apply with pencil and paper the hashing algorithm that Bitcoin is actually using, SHA-256. There's another training session last week or 2 weeks ago about hashing. I think that Nakov was the trainer there. We are going to see only the one that the Bitcoin network uses, which is the SHA-256. When I said that we would like to have hashing and do some work by validating the transactions and bunching them in a block, we're going to see how it happens actually in Bitcoin. As I said earlier, we are supposed to have a consensus about who is capable to add a new block and how to make sure that the block that someone is trying to add is a valid one. This is happening due to the proof of work. So the miner is actually providing some proof of work that he or she spent some time trying to solve the cryptographic puzzle. Later we are going to see what is a cryptographic puzzle, but we could give an example. Let's say that we're here and we're all students in a math exam. So the first of us who is going to solve the mathematical problem, but not only come up with the answer, but all the steps that he made until he get that answer, is going to win the prize, the award. That student is going to need a lot of brain power, and then actually he is going to need some energy. Let's map all set until now to the cryptographic world. Basically all the students here are going to be the computers or hardware, computing hardware. The classroom itself is the world. The mathematical problem that we are going to solve is actually a transaction that we are going to try to validate. And then the brain power that the student is going to use is actually the computing power of the machine. In the end, all the energy that we spent is going to be the electricity. Pretty much that's how proof of work works. The fastest miner who actually solves the cryptographic puzzle is going to take the award. Currently we said that it's 12.5 bitcoins, and he might take the transaction fees as well. So we have two types of rewards, but we are going to see them in the next slide. So the proof of work actually is a mechanism that shows that the miner did spend some time actually trying to solve the cryptographic puzzle. In the end, the reward is given to the first one who actually, with luck, with a lot of calculations, stuff like this, managed to solve the puzzle. And all the miners compete with computer power to be the first to find the solution, the right answer. That's the first consensus that is used in Bitcoin and Ethereum right now. They use different proof of work algorithms, but that's pretty much it. The other consensus algorithm is the so-called proof of stake. The Ethereum network is going to move from proof of work to proof of stake with the next Casper update. We don't have a release date right now, but for sure it is going to move to proof of stake. What are the differences between both of these algorithms? Proof of stake is energy saving. We don't need so many miners to compute and solve these puzzles. That's why it's energy safe. Proof of stake is about getting a bunch of validators, which are the so-called miners in proof of work. Here we have validators, or the so-called forgers. Actually, if you take the Ethereum wiki, for example, it is written that if you would like to become a validator when it moves to proof of stake, you should execute a special transaction to the network, which is actually depositing amount of the coins of the network. It's a deposit just to make sure that the validator is not going to lie, is not going to fake the network. The deposit is the stake actually. So we are going to have a lot of validators as well again, but they are going to be awarded only with transaction fees. No new coins are going to be mined and added to the network. This is one of the things that Ethereum are about to make. Currently, Ether doesn't support the hard cap. I mean that there's no fixed amount of Ethers in the network, but when they are going to move to proof of stake, they're supposed to put a maximum amount of the network coins. So proof of work, we have a lot of miners who compete with computing power to solve the cryptographic puzzle in order to get the award. Proof of stake, we have a bunch of validators or forgers who actually deposit coins to the network to make sure that they're going to secure the network, and actually they're going to vote which is going to be the next valid block. So that's a little tricky, as at some point if we have a fork in the network, there are going to be some penalties or fines to the validators who doesn't support the main chain. But it depends again on the cryptocurrency and the algorithm that stands behind it. The proof of stake was initially mentioned at 2011 at the Bitcoin Talk Forum, and the first coin that implemented this algorithm is Peercoin actually in 2012. Bitcoin and Ethereum, as we said, they use the proof of work. Mining Bitcoin is the next thing that we are going to see. Here we're going to see what it's like to get an input and then apply SHA-256 on it. When it comes to mining Bitcoin, we talked about a cryptographic puzzle. So a valid transaction here is a hash that is provided by the miner with a fixed amount of leading zeros. We are going to see an example right now when it comes to hashing, but it's really hard to find a string, a number, that when we hash it and apply SHA-256 on it, to get a string with a fixed number of zeros in the very beginning, leading zeros. We are going to try with hello world, stuff like this, just to make sure that we find the first string that we have like 3 or 4 leading zeros. Right now, a valid hash in the Bitcoin network is considered a hash that starts with at least 17 zeros. So we are not going to get this example, as this computer is not gonna make it today. That's why we are going to try with some small numbers, just to make sure and see how it works actually. Okay, so the cryptography itself, we are going to see that simple input like hello world, in the end we are going to see just a bunch of letters and numbers, which is nothing to us. It means nothing. That's the idea here, that Bitcoin is using one-way cryptography. I mean that it's pretty hard to find a hash that starts with a fixed number of leading zeros, but it's very easy to be checked. I mean that if we find a number that got like 4 leading zeros, it's very easy for us to check if this is the correct answer. So that's pretty much it. We spend a lot of time trying to find the correct answer, and we could check the answer in less than a second if it's the correct one. This is how the Bitcoin works in simple words: validating transactions and calculating hash. No, we don't need this one. Okay, here's a SHA-256 hash calculator, and we're going to see if we input, for example, hello world. This is the applied hash of the input string. So no matter how many times we type hello world, the final result is going to be the same. If we change a simple word, let's say that I'm going to type this with a small w, we are going to see that the final result is totally different. In Bitcoin, the hashing algorithm actually applies the SHA-256 twice. We have double SHA-256 applied on the input that we have. When we say blocks, validating transactions and stuff like this, I'd like to show you how actually a block in the blockchain looks like. I mean, everything in yellow is actually the information that we have in a block. We have a version, we have the previous block hash, we have the Merkle root with all the transactions inside, we have the timestamp, bits and nonce. This number nonce is the one that miners are trying to guess. I mean that you could see the block hash in the end. This is the applied SHA-256 on this data in yellow. So we have all that information, And as you could see, if we change a single letter or number, the final output is totally different. So actually, when it comes to mining, in order to get the next valid block, the miners are trying to guess the nonce number, get the final hash of the block, and the hash of the block is supposed to be less than the difficulty in the network. The difficulty in the network is a large number which is trying to keep the time frame when it comes to mining, adding blocks, to a strict frame. In Bitcoin it is 10 minutes, so we know that every 10 minutes we have a block. So the difficulty number actually plays the role of keep that time frame. I mean that if the difficulty is very low, we could add blocks in a second in the network, which is not the case. The Bitcoin blockchain is trying to keep that time frame, as the value of the Bitcoin is going to decrease dramatically if we add new Bitcoins to the network very easily. As I said earlier, for each mined block we have a reward of 12.5 Bitcoins plus the transaction fees, and this is going to be reduced over time. It is reduced actually every 4 years, or 210,000 blocks. That's the algorithm, and around 2040 we are going to hit the hard cap, and there will be no more Bitcoins, new Bitcoins added to the network. But let's get back to this one. As we said, every miner is getting a bunch of transactions and is trying to validate the next candidate block that must be added to the blockchain. This is the information that every block has, and the first of the transactions in the list is the so-called coin-based transaction. It's a special transactions that, let's say, that's Precious miner, and it is set in the coin-based transaction. If the block is valid, give or send to Precious wallet 12.5 Bitcoins. So the first transaction in the candidate block is actually the reward for the miner, and the rest of the transactions are all the transactions that happened in the network during validating this block. We have a transaction pool that every miner saves this pool while trying to validate the block. We have the previous block and we are trying to validate the next one. We have some transactions over the network that happens, and if another miner validates the block, all the miners have to update the local copy of their transaction pool, remove all the transactions that are put in this block that is validated, and the rest of them, they just try to mine the next block and validate it. But the point here is that with this nonce number, we are trying to adjust the final hash of the block, which is the answer of our cryptographic puzzle. As we said, currently all transactions with, it used to be 17, I think that right now they are supposed to be 18 leading zeros. So everything with 18 leading zeros as a number that is below the difficulty of the network is considered to be a valid block and a valid answer for the puzzle. In a couple of minutes we are going to see how hard it is actually to find the number, a string that produces a hash with a fixed amount of leading zeros. We started with hello world, for example. I think that this is an example that I uploaded to JS Fiddle. and here we could input some names, and then we would like to see how difficult it is to find a hash with some number added to this information and produce a hash with a fixed number of leading zeros in the end. Let me just, okay, this is going to take some time. I put 5 as leading zeros, and let's see if we are going to make it today. Basically, when it comes just a second, as I have it over here. So the example is pretty much trying to get the difficulty, or how many leading zeros we are supposed to have at the beginning of the hash, and we would like to see the time that the machine takes to find the first hash with this fixed amount of leading zeros. You see that when it comes to 5 leading zeros, this machine took like 15 seconds to find a number that must be added to the input we have in order to produce a hash with 5 leading zeros at the very beginning. As we said, right now we are supposed to have like 18 leading zeros, which is a huge number. I cannot run something like this here, but in the end I could provide you a link. You could play with it. The idea here is that we have some information at the very beginning. Here it's just count and some names as a data. It's pretty much a basic example that we would like to see if we apply some changes on this input, when we are going to get an output hash with a fixed amount of leading zeros. So in the below this function is the original SHA-256 as a hashing function. We are not going to step into it. It's public, you could check it and play with it. We are going to play with it in the end, where we are going to change hashes manually with pencil and paper, just to see what is the mechanism behind the SHA-256 as a function, how it is applied, and what we actually do in order to change the input and produce the fixed output. I said fixed output, and it is always 32 bytes in output that we have after executing this function. We saw that with hello world we have no success with leading zeros, but if we start trying with 1, 0 and stuff like this, we are going to get a point, but I'm not quite sure when. We have to play a lot, but if you start playing, I think that the first attempt with hello world is about 1400 and something times. We have to do this in order to get a result with 3 leading zeros, with 3. You could play a whole day just to find a result like this, that the output hash is with 3 leading zeros. So when it comes to manually doing it, it's obsolete. Something else about this one, we are going to see it later, the mechanism and how the data is changed when applying the function over it. But the Bitcoin network uses this function for encrypting the data. We're not going to step over this block. We are going to use the number here later in another example, just to try to mine the next block when we have all the information from this one.
Is the fixed length?
Yes.
8.
Yes. And this is the only thing that we have to update while trying to validate the block to find the correct answer.
But it's not a hash.
No.
Explained it.
Yes. Okay. As we said so far, miners actually validate new transactions. They secure the network and record all the valid transactions into blocks on the ledger. It's all public. As I said, we have a block that is mined every 10 minutes. All the miners compete to solve a difficult cryptographic puzzle, and this is actually the answer of the cryptographic puzzle is actually the so-called proof of work. That's the proof that they did spend some time trying to find the correct answer. When a block is solved or validated, it is added on the blockchain. The transactions are considered to be completed, they are valid, so in the next 10-20 minutes the bitcoins from all the transactions could be spent. We're going to calculate the total amount of bitcoins that are going to be supplied with a simple code. As I said earlier, currently the reward for validating a block and adding it to the blockchain is 12.5 bitcoins. At the very beginning it was 50. So having all this information that every 210,000 blocks the amount is halved. At the very beginning it used to be 50. After the first 210,000 blocks we have an award of 25 bitcoins. After 4 years or another 210,000 blocks, we have the reward that is currently 12.5, and over the time it's going to become 0. As we said, this is supposed to happen around 2040, and at this point all the miners on the network are going to be awarded only with the transaction fees. There will be no bitcoins. Може? This is written in the protocol of Bitcoin in the very beginning. So it's like steps until all the bitcoins are mined and are available in the network. The code is really simple. Here we could see that we have the starting reward, which is 50 bitcoins. We have the reward interval, which is 210,000 blocks. We said that every 4 years or 210,000 blocks, this is halved, the price I mean. When it gets 0, we're going to see that no more bitcoins are going to be mined. They're not, and the total supply is reached. The output here is 21 million bitcoins. This is going to be the total amount of bitcoins. We have, if you wonder what is Satoshi, that's the smaller value of Bitcoin, by the way. But with this small piece of code, we could easily calculate that the total amount will be around 21 million Bitcoin. Here, you could see the awards that is going to be given for validating a block over time. Right now we have like 12.5 bitcoins as an award for validating a block, and as I said, with all the new mining hardware that is added to the network and so many miners, around 2040 we are going to hit the total market cap for this one. Mining rewards, we have like two types. The first one, as we said, is when validating a block, the miner receives a fixed amount that is right now 12.5 bitcoins. In Ether, I think that right now it's 3 Ethers. It used to be at the very beginning 5, but they updated the network last October, I think, and the amount is changed. The other type is actually keep the change, or this is the transaction fee that the miner is actually getting. So when we have no more bitcoins, this is going to be the only way of rewarding the miners. We'll only have the transaction fees. Over time, these fees might become bigger. So we're going to see if the network is going to keep the miners. We already saw this one, how to calculate the max amount of bitcoins with some code. That's pretty much it. In the end, we have the amount in bitcoins and satoshis, which is the smaller one. Here's the question: if we could mine SO or join a pool, and what this means actually. Nowadays, let's say that SO mining is not a way. You're going to waste your money and you could wait for years to mine something. In the very beginning, when it comes to solo mining, you were able to mine with a hardware like this one, for example, to mine bitcoins. With CPU or GPU, it doesn't matter. But what
когато попадаш примерно в пул и в транзакциите имаш някакъв смарт контракт, който трябва да изпълниш, кой го изпълнява? Самия миньор или самия пул го изпълнява? Смарт контракт.
Самия миньор.
Самия миньор изпълнява смарт контракт.
Да.
Тоест софтуера на миньор, с който попада не е въпрос просто хешове да прави и цялата виртуална машина трябва да е вътре в него.
Да, това е малко по-различно. Now we are going to see a pure example of applying SHA-256 over an input. All the inputs here are hexadecimal numbers. There are some constants that are defined in the function that we are going to use, and the only thing that is actually the input is this letter over here. We saw it a couple of slides ago. It used to be the version of the block. That's a number that we are going to take, for example, just to see that with all these numbers here that we have, how we are going to apply the function and how we are going to hash all this data here. I wanted to draw it here, but probably I'm going to use Excel just to make sure and show you how easy it is actually to apply SHA-256 over input. This is not going to validate a block, of course. We have to spend a lot of days, years maybe, just to validate a block. We are going to show it with small numbers, just to show how the function works actually, what are the steps. As everything here is about calculations. That's mining. We have to find the nonce that we have to put together with the rest of the data from a block and find an output hash with a fixed amount of leading zeros. That's pretty much it. So now I'm going to open the Excel. Okay, first of all, this is something that we saw as a number. I'm going to take these 8 variables. They are from the SHA-256 document. We are going to use these constants and apply hashing over our input, which we are going to take the version of the block. This is going to be our input as a nonce, and the rest we are going to take from here. We are going to see what are the steps actually in order to get the final fixed length of the hash. Now I'm going to put like just a second. I'd like to make it like this. I have it written over here, but I'm going to explain it. I'm going to input these constants over here. We always have like 8 blocks of input. We are going to have 8 inputs here as constants that we saw over here. And in the end, we are going to get our nonce or number that we are going to take from the block version, and we are going to see what are the steps actually. I'm going to name these blocks over here A, B, C, D, E, F, G. Okay, we have like A, B, C, D, E, F, G, and H. Okay, now I'm going to write the values that we have here. It's like 6, A, 0, 9, Good. That's the first constant that we have. We're going to input the other one. B 67 E 85. Now we have 3 C 6 E. One F 83 D 9 B, and we have the last one 5 B E 0 C D 1 9. Okay, these are actually these constants over here. Now we would like to convert these hex numbers to binary numbers. We are going to see, okay, I'll put it right here. We have number, there's like decimal number, then we have like hexadecimal number, and in the end we have like binary. We are going to see all the numbers up to 15. Okay, and then we have the binary representation. We have like this. This is 6, 7, 8. Okay, we would like to convert everything here to binary decimals. Okay, 6 equals to A equals 0 is actually 4 zeros, 9 is like this, E. We have again 6, 7 is like with 3 ones. Okay, we have B. We have again. That's the first step, that we have to make sure that converting all hexadecimal numbers to binary. Okay, now we have like 0011, 1100. It's like E, F. Okay, these are A, B, C. We have D, E, F5, Okay, this was the first. What? Okay, 9 is okay.